Hi, good afternoon, everyone. Welcome to the 8th Space Ventures webinar. Before we go any further, I'm just going to do our standard thing. Can you please write where you are joining us from today in the chat box on the right-hand side? Brilliant. That seems to be working. That's great. Many great places there. Okay, to begin, my name is Tahid Khan. I'm a VP at Surface Ventures, and I'm your host for today. Just to give a bit of background about ourselves, we are a non-for-profit organization, and our mission is essentially to provide world-class surface engineering education for academia and industry. So every month, we bring you a sector-leading speaker to present the current challenges and future trends in surface engineering. So today it's my pleasure to introduce Professor Daniele Dini and Dr. James Ewan, who will be talking about virtual experiments in tribology. To give a bit of background on our speakers, Professor Dini holds the post of Professor in Tribology. He's the head of the Imperial College Tribology Group, which is one of the largest tribology groups in the world. Professor Dini's research centers on the application of advanced modeling strategies to applied mechanics, materials physics, chemistry, biomechanics, and structural integrity, with a particular focus on tribology. Dr. James Ewan is a Royal Academy of Engineering Research Fellow in Tribology Group, part of the Department of Engineering at Imperial College London. James uses supercomputers to study solid-liquid interfaces with molecular simulations. He studies complex formulations to identify links between their nanoscale behavior and the macroscale performance. So in terms of today's agenda, as always, we'll start with the presentation and then switch for a few minutes to our sponsor, who is Micromaterials, and then we'll come back to our presenters for your questions. We are planning to go for around 60 minutes in total today. However, depending on questions, this may go over, so please do bear with us. We will provide a few brochures. There'll be option to get some brochures from Micromaterials and further information later on in the talk. And a reminder regarding our website, which is surfaceventures.org. It features videos from our previous talks, information regarding upcoming webinars, and information regarding the Surface Venture team. So we always like to know a little bit about yourselves. So we're going to put a quick poll, like we like to do, and if you could answer the question that should pop up on your screen right now, which of these currently best describes your current position? Brilliant. We've got a nice mixture of results there. That's great. So on that note, I'm going to hand over to our speakers, Professor Dini and Dr. Ewan. So over to you guys. Thank you very much.
Hello. Hi. I hope you can all hear me. I'd like to start thanking Surface Ventures for having us and inviting us to this seminar series. I'm particularly happy to be here as someone who's spent the last 20 years developing models for tribology. And certainly, I hope we can show you some of the beautiful things you can do with those. And I'm very pleased that one of the architects of those models is accepted to join me into providing part of this presentation. So James, over to you.
Thanks, Daniele. So I'll get right to it. So I'm James. So tribology as a subject is all about reliability historically of machines, and more recently with concerns with CO2 emissions, concerns with energy efficiency are becoming more and more important. At the component level, the things that affect these are friction in terms of energy efficiency and wear in terms of lifetime and reliability. and collectively these are responsible for nearly a quarter of global energy consumption. So this obviously motivates a lot of work in tribology and means it's incredibly important. Most tribology research is still macroscale experiments, which try to replicate the conditions inside these components. So you've got a sliding rolling MTM on the left, a reciprocating HFRR in the middle, and a roller MPR in the middle, on the right-hand side. And what these try to do, as I say, is to replicate the conditions inside tribological contacts to try and either formulate new lubricants or new materials and coatings. So tribology is an extremely complex subject, interdisciplinary. Inside a tribological contact, you've got many competing processes going on. Some of these are represented in this schematic here. What becomes clear when you're studying a tribological contact, it's a multiscale and a multiphysics problem. So there's lots of different scales at play, right down from the molecular scale up to macroscale phenomena. And there's lots of competing physical processes, which may or may not be important to the performance indicator that you're interested in for the different topics. And another challenge in tribology is that often behavior at the smallest scales is very important to the macroscale performance. And I'm going to talk a little bit about that a bit further down the line. So as I say, as Daniele briefly mentioned, so we in the tribology group at Imperial do a lot of modeling as well as experiments. These span right down from the electronic and molecular scales, right up to the continuum component level modeling with CFD and things. Most of my research personally sits somewhere in the middle. Daniele sits somewhere up towards the top end with also molecular scale stuff, and we'll talk about different techniques that we both use in our research. One topic that kind of is relatively new in tribology and is becoming a bit of a hot topic in various different areas is the concept of the digital twin. So the digital twin is effectively just a virtual representation of a physical object. There's lots of kind of buzzwords that go along with that, things like big data, cyber physical systems, industry 4.0, machine learning, artificial intelligence. All of these are kind of interrelated concepts. I won't go into in much detail in this talk, but just briefly introduce them and how they could be useful in tribology. So you may ask how digital twins are different from the kind of types of physics-based modeling that we're very used to in tribology and that we've been doing, as Daniele says, for many years. So the idea behind digital twins is to combine physics-based simulations that we're used to with data-driven approaches and emulation. So not just simulating processes inside tribological contacts, but using data-based approaches to emulate what's going on, basically because it's cheaper than physics-based approaches. Essentially, another important component is that there's continual feedback between your experiments, whether they be laboratory-based experiments or continuous monitoring of real machines and vehicles. There's continuous feedback from those into the virtual world, and then information is sent then back into the experiments in a continuous feedback loop. So that's something that's different from kind of conventional modeling. Just in terms of a bit of a history, arguably the first digital twin was actually Apollo 13, the NASA mission. Many of you may have seen the Hollywood film. Essentially, an explosion in the oxygen tanks meant that there was a critically damaged engine, and NASA had to essentially replan a route to get the spacecraft back and the astronauts back safely to Earth. You may have seen in the film that they had based at NASA, they had computer-controlled simulators which emulated the spacecraft, and they used those to basically replan the mission to be able to get back with the resources that they had. And there was a continuous feedback loop between those simulations and the real-time data from the spacecraft as to their position and speed. And fortunately, they managed to successfully re-enter, and all was well. A more recent application, ECMWF, which is the European Centre for Medium Range Forecasts, is to create a digital twin of the entire Earth system. So that's the Earth, the ocean, and the atmosphere. And essentially, these models work by optimally combining simulations, which are mostly physics-based, but also data-driven stuff, with near real-time observations from satellites and planes and other things. To continually look at the state of the Earth's atmosphere to be able to predict what it'll look like in the future. And there you can see in the figure is just a representation of an observation and a simulation using this technique. You may have also seen that I also organise a tribology based seminar along with Chiara Gattinoni at ETH Zurich called West Tribo. In that talk, you may have seen there's already been some digital twins work in tribology, both at SKF and at Shell. So Victoria Van Kamp's talk from SKF and Ian Taylor's talk from Shell both discussed how digital twins may be useful in tribology. So if you haven't seen those out, but essentially just to sum that up briefly, so SKF are a bearings company, and they plan to use and are already using digital twins approaches to predict maintenance and lifetimes of bearings. Shell are using it more for optimization purposes of their fuels and lubricants. And there's other companies doing that. So General Electric and Chevron, for example, for wind turbines, and Rolls-Royce to optimize aircraft engines. So there's many already industrial applications of these approaches. And it's something that's becoming increasingly commonly studied in academia as well. So briefly, just to borrow something from Ian Taylor's West talk, essentially. So to create a digital twin of not even a component, even just of a tribometer experiment, is quite a challenging task. You've obviously got to know the conditions as you do with your model, so your load, your speeds, your temperatures, etc. You've also got to know the details of the surface materials, so the hardness, roughness, surface chemistry, etc. And they obviously continually evolve, particularly during the running in phase. So you've got to continually monitor those and feed them back into your models to understand and correctly predict what's actually going to go on in the future in terms of performance. And you've obviously got to know about your lubricant as well, so the viscosity, additive chemistry, how tribofilms are formed and removed continually during operation. And again, that requires some feedback from the experiments to continually monitor those forming and being removed. So yeah, briefly, I'm going to talk a bit about some atomistic modeling that we've done in the tribology group, that's essentially trying to predict macroscale performance for some very well-defined systems. So not fully formulated lubricants, but simple one or two component systems where we know very well what's going on in terms of surface chemistry and things, quite well experimentally characterized, which allows you to kind of more easily input that into a model in a way that's representative of the actual experiments. So the first example that I'm just going to briefly go over is in the boundary lubrication regime. So quickly to go over a Strybeck curve for anyone who hasn't kind of done a lot of tribology. So on the left-hand side of the Strybeck curve is where the load is mostly supported by the surface asperities, so from solid-solid contact. And the far right-hand side of the Strybeck curve is where the surfaces are now well separated through fluid entrainment, and the load is mostly supported, completely supported by the fluid film. In the mixed lubrication regime, which sits in between those, load is partially supported by both the asperities and the fluid. That's a kind of more complex case, which I'll come to later. But here in this case, we're just looking at the boundary lubrication regime. So we know that there's no real fluid entrainment, and that the surface sliding surfaces are only either separated by solid-solid contact, or in this case, the contact of additive films which are adsorbed onto the surface. So these are the additives that I'm talking about just here briefly are organic friction modifiers, which have polar head groups and non-polar tail groups. They adsorb to the solid sliding surfaces and form monolayers. And those monolayers are actually quite strong, although they're very thin. They're only about 2 nanometers thick, but they're strong enough to maintain separation between the surfaces in the boundary lubrication regime, and that significantly reduces friction and wear. So that's been known for a long time. What I did at the start of my PhD was to look at the effect of surface coverage and different OFM types on OFM friction in these types of systems. So what these simulations look like are essentially just 2 solid surfaces, which are in this case alpha hematite, so iron oxide, representative of steel, and then 2 monolayer films on the opposing surfaces with the head groups attached to the solid surfaces, quite strongly adsorbed. They're not grafted, but they do have strong interactions with those surfaces, and then a thin layer of lubricant in between. I should say, yeah, and so the pressure is added to the top wall essentially, and the 2 walls are slid in opposing directions just by adding a sliding velocity, and that's essentially common in non-equilibrium molecular dynamics, which is what we're talking about here. So what we found was that essentially at high surface coverage, you form solid-like films, and you can see there, so that the orange line is the mass density profile through the fluid film for the friction modifier. The blue is the same for the lubricant layer, and the purple line shows the velocity profile of those layers. So you can see that the friction modifier layers move essentially at the same speed as the surfaces, and you get clear slip planes between the different layers at high coverage. When you get to medium and low coverage, you essentially get shear of the whole system. There's much more interdigitation between the blue lines and the orange lines, which are the friction modifier and the lubricant, as I say, and you essentially get a more couette-like profile. So you get shear of the entire system, and hence more viscous dissipation. So quickly, just to show that the friction in the low coverage case and the medium coverage case are much higher than in the high coverage case, where you've got clear separation of the layers. Danielle, if you could just play the first video. Yeah, so hopefully you can see the video. This is the low coverage case, just showing how essentially there's no clear separation of these layers. There's lots of interdigitation between the lubricant and the friction modifiers. And you get quite high friction in this case. If you could just go on to the next one, please, Daniele. And here you can see, on the other hand, that you've got very clear solid-like friction modifier layers. You can see that there's clear slip between the bottom of the friction modifiers and the lubricant there in the middle, and that's the case that gives much lower friction. And if you could just go on to the next slide, please. Yeah, and the next one. And yeah, this is just a comparison to some experimental data. So this is a CETR UMT2 experiment, which is essentially a boundary friction experiment where you can run at very, very low speeds and quite high pressures. So in these experiments, you're quite confident that you've not got any fluid entrainment, so that the friction that you get is purely from the solids rubbing against each other, separated by whatever strongly absorbing additive you may have there. So in this case, these friction modifiers. So on the left-hand side is the experimental data, and on the right-hand side is the non-equilibrium molecular dynamics data. So they're separated by several decades in speed. That's a log. So on the bottom of the x-axis is a logarithmic axis. So the sliding velocities that you use in the NEMD simulations have to be much higher than they are in the experiments. The reason for that is that to reach a non-equilibrium steady state in the available simulation time, which is the order of nanoseconds and not very long at all, you've got to run quite fast to get basically a converged friction coefficient in the time that you've got. So that's commonly known with NEMD simulations. But what's nice is that because you can apply a very efficient thermostat to the walls in this case, you can suck all of the frictional heating that you would get experimentally at these speeds out of the system. So you're basically still in an isothermal case. So it's quite good to compare directly to experiments. And you can see here the extrapolations from the experimental data conducted at low shear rates is in very good agreement. The red and the blue line are for stearic acid, which is a linear chain. As you can see there on the bottom right-hand side, they pack very closely and very densely, like the high coverage case that we've got in the simulations. And you can see that there, the purple and the red and the blue all agree quite nicely. And essentially that was a confirmation that the stearic acid is able to form these high coverage films and get to this low coverage case where the friction increases basically logarithmically with sliding velocity. On the other hand, oleic acid, which has this kink in the middle of the chain, can't form these high coverage films. You can see on the right there that it can only form low coverage. This was confirmed by some powder adsorption experiments and polarized neutron reflectometer experiments at Cambridge by Stuart Clark's group. They can't form these high coverage films, and essentially you get a much higher friction coefficient, which is less dependent on sliding speed, which is in agreement with the experiments for oleic acid. So that was another quite nice confirmation. Just to go to the extreme other end of the scale, so in full film elastohydrodynamic lubrication, essentially this is important in components which slide and roll together, so things like rolling bearing, CV joints, and cam follower systems. Essentially here you get solid deformation of the solid surfaces because the pressures are so high, and you get relatively thin lubricant films which separate the surfaces. All of the conditions I'm going to talk about are above the film thickness, well, above the lambda ratio, where surface roughness affects friction coefficients. So basically, there's no roughness effects on friction. It's just purely from shearing of the solid from the solid-like lubricant film. And essentially, yeah, so what we did in this study was, again, compared to some NTM friction experiments. So this is a rolling sliding friction experiment with a ball and a disc with separate motors to get any slide roll ratio that you want. And what we did was to compare the friction from experiments and from NEMD simulations of traction fluid like molecules, which are these bulky ones in the middle. So DM2H and DCMP, they're both traction fluids. So they're actually designed to give high friction for use in traction drives. And squalane and diethyl hexyl silicate, they're a hydrocarbon oil and an ester oil, and they're designed to give low friction, as they're commonly used as model lubricants. So we studied all of those in both the experiments and the simulations. And what? Oh, sorry, if we could stop the video a minute. Oh, yeah, that's right. Yeah. So what we found was, again, the experiments, you can't go up to high shear rates without getting significant shear heating. So these are thermally corrected friction coefficients, I should say, as well. So you basically run at lots of different temperatures and then interpolate those to find what the friction coefficient or shear stress would be without shear heating. And when you do that correction, you find, again, very good agreement between the experiments and the NEMD simulations for these different fluids. So again, the friction for the lubricants is much lower, but it increases more with sliding velocity, so it's more sliding speed dependent. Whereas for the traction fluids, friction is much higher, so it shoots up at low drain rates or slide roll ratios, and then reaches basically a steady state value that it stays at no matter how high you go in pressure or sliding velocity. That's something that's called a limiting shear stress, and it's something that's not massively well understood. But essentially what we did here was also to look at the flow inside the contact. So again, this is a mass density profile overlaid onto a velocity profile. And what you can see is that at low pressure, you get the expected cuvette-like profile, where essentially you've just got a linear profile between the two sliding surfaces. But as you start to increase the pressure, you start to get this central localization or shear banding behavior, where the outer layer of the fluid basically moves at the same speed as the wall, and the shear occurs in the middle of the fluid only, as the friction coefficient starts to flatten out. So as you start to reach this limiting shear stress like behavior, you don't quite get there with the lubricant at these pressures, but you start to approach that. Let me go to the next slide. There we go. For the traction fluid, you essentially, even at low pressure, you get some central localization. So the flow isn't cuvette-like even at low pressure. And as you start to increase the pressure, you transition to this plug slip-like behavior, where you essentially get shear close to the surfaces, but not at the surfaces. And the middle of the fluid isn't sheared at all. So you get like a plug-like flow. I'll quickly just show you some videos of what those look like. So the first one, this is the central localization. So this is squalane at kind of an intermediate pressure. And you can see quite clearly that the layers close to the solid surfaces here are basically moving just with the surfaces, and all of the shear is happening in the middle of the fluid. So that's where all the shear occurs. And if you just go to the next one, please, Daniele. And this is the plug slip case. So you can see that the first layer of fluid is moving with the walls, but then the layer of fluid above that is basically there's a slip plane forming, and there's not much shear going on there at all. And in the center of the fluid, it's basically glass-like and not shearing at all. So that's the high pressure case. And yeah, if you stop that one. What's more challenging from a molecular point of view is this mixed lubrication regime, as I mentioned before. So here the load's partially supported by both the solid asperities and also by the liquid lubricant. And because surface roughness has kind of a fractal-like character, there's some stochastic nature to this that's difficult to predict. So you need essentially mixed lubrication models which tell you where the asperities are, how much asperity contact is occurring under the conditions, what those conditions look like at the local level, and you need lots of information which isn't easy to predict, essentially, isn't easy to measure in an experiment, and isn't easy to replicate in a simulation. So essentially what that means is that you have to do some form of coupling to larger scales, whether that be contact mechanics models or Reynolds-like models for fluid flow. And there's many different ways that you can do that. Concurrent coupling or hierarchical coupling. So concurrent, where you're coupling the model, the atomistic model, directly to a continuum model, or hierarchical coupling, where you essentially pass information through separate molecular simulations into a larger scale model. We do both of those, which Daniele will talk briefly about. But yeah, I'll pass on to Daniele now to talk a bit more about the continuum scale, continuum scale, and some coupling to the molecular scale as well.
So what I'm going to do here, I'm going to take over from James just to give you an overview of other beautiful things you can do with models when you look at slightly larger scales. And I'll start with the application level scales, where you really want to look at the engineering response of different systems. So the typical example, classical engineering, is looking at trying to reduce friction in engines, although some of these engines will be disappearing soon thanks to the energy transition, but there's still plenty out there. And one of the ways to optimize energy efficiency is to try and reduce frictions where it is generated. And in the engine, and most of it comes from piston liner interaction between various components. So looking at that and looking at how you go about modeling this, one of the things we always do as modelers, I'm one of those modelers who doesn't believe in modeling per se. I think we always need to relate what we do with experiments. Just like James showed, even at molecular level, you need to try and understand how it matches the experiment. So we started looking with Tom Redioff, one of our colleagues, at the replicating what happens there with an experimental apparatus. And the idea was to have a system that mimics, for example, a piston ring sliding over a cylinder liner, and to be able to see through, to explore what actually happens in this setup. And the idea was to try and see if the models we developed would explain, for example, the effect that putting a texture on the surface of the cylinder liner would do to reduce friction. So what we did was first to simulate these systems. And as you simulate the system, here you have a texture surface which is being interposed between, which is interacting with the piston ring, and you can see as the pocket travel through, you can see some cavitation emerging as you do reciprocating sliding, and this texture interacts with the ring, and you can see that these interactions are substantial in terms of pressure and changes in the dynamics of the system, including when you start and stop. And the idea is that this texture has been demonstrated for now a couple of decades that improve friction performances. And the idea was to try with models to understand why. So as I said, without experiments, it's very difficult to see if your models are going okay. So what we do usually is we try and relate our models to experiments. So in the rig that you've seen, I've shown you in a couple of slides before this, you saw that we have this setup whereby there is a camera as a transparent cylinder liner equivalent with the texture on it, and you can actually view through that to see what happens at the interface as the fluid flows through. And the idea was that if you can see what happens at the interface, we can start looking at the mechanisms that are responsible for this friction reduction and try to see if we can match our models with that. So our models can help interpreting what's going on. So this is what happens. So if you slide up and down, you'll see, because this is a fluorescence experiment, you see the areas which are brighter is where there is more fluid. The areas which are darker is where there isn't very much. And you can see also this very nice formation of bubbles. You can actually see this cavitation happening and also see the interaction between the texture and the film forming. And you can see also as you reciprocate, and velocity has a strong effect on this. In this respect, if you go back and try to simulate all of this, what we managed to do is to try and do a model which is as accurate as possible. So in order to mimic this, one of the problems that we had is that you can't just do a simple model where you just look at the hydrodynamic flowing. You need to look at the real interaction between the solids, their actual the shape of the system, the way the texture affect the fluid flow, and the way the roughness also plays a role. Since here we'll be talking about all the regimes from hydrodynamic to boundary, because as you reciprocate your motion, you end up having, as you stop and start, you have boundary lubrication. As you go in the middle of the stroke, you end up very close to hydrodynamics. And if you modulate the speed, you can actually go even farther into the hydrodynamic regime. But the idea is was to explore what was seen as a good benefit, especially in boundary lubrication, from the use of these textures. And to do this, I mean, we end up, well, you can do this in many different ways. The way we used to do is, we use generalized Reynolds equation. We have the condition where temperature rise is not really significant. And we also explicitly model the presence of roughness to see whether or not it's got a particular effect, especially towards the boundary. Now, as I said, these models are fairly complicated, but ultimately allow us to do a lot of interesting observations. So, for example, if you look at modeling the texture passing through the contact, here you'll see the film thickness evolving as the texture goes through the contact on the top left-hand side. And you can monitor at the same time the hydrodynamic pressure, the contact pressure, and the displacement, which actually tells you the film that you have on the bottom left. And the idea is that as the pocket travels by, you'll see that many of these quantities change. Most noticeably, on the bottom left, you see the normal displacement. You see that the effect of the traveling texture has an effect on the liftoff and the film. You can also see that at the same time on the bottom right, the friction is highly affected by this. Now, the thing that is probably one of the most counterintuitive here is that as you go boundary friction, the change in liftoff on the left-hand side is tiny. Is the blue line is the lowest speed we're running at, but the change in friction is the most significant. So it's the same as the blue line on the bottom right. And how to explain this goes back through to the fluid mechanics of the system, looking at the simulations that we've done and try to understand exactly what goes on. So we've done simulations which are very detailed. There's a lot of information. You need to model the textures properly. You have thousands and thousands of nodes. I'm not going to go into those details. But the important thing is that if you now do a proper model, one of the things that you see is that you can see this effect of different fluid entrainment within the pocket. As the pocket passes by, there is some different effects due to fluid entrainment. And this is very important. For example, if you look at the full film, when you go faster, you form a full film. As the pocket travels through, you have this entrainment, inlet suction. This is the blue line on this graph. And as you go by, then there is an exponential decay of this, and it's very prominent. So you see that here there is a lot going on. And as you go into slower speeds, so you stay almost in, you don't have enough speed to form a full film. You end up in what is sort of mixed regime. You see also there the yellow curve shows that there is an increase in film as the pocket goes through. But what you see in the boundary is that in the boundary regime, which is red, you go slow enough not to form a film, so you stay boundary throughout the experiment as the pocket passes by. There's a tiny increase, there's a tiny liftoff, there's first a little suction of fluid and a tiny liftoff. Now, you might think, okay, well, that cannot make a significant change. Well, in reality, that is what actually is responsible for the increased performance of the system, because to put it very simply, a change of 20% on something very small is in terms of, at the moment, if you don't have any asperities, lots of asperities are in contact and you don't have any film, increasing the film by 5-10% has got a massive differential with respect to not having the film at all. Whilst if you're already in hydrodynamic regime, actually increasing the amount of film sometimes could bring back to more viscous losses as you're adding more fluid that you need to shear. So, and this could be, not only is the reason for that, but also it could be verified that the inlet suction, even in this condition, the one that we see in the videos from the movie I showed you before, it seems to be corresponding to the exact situation that we model in our system when we put the full mixed elastodynamic lubrication together. This is a beautiful example where something that potentially it's fairly complex can be unwrapped into the different aspects so that you can actually understand it better. And in fact, this is what You can see here, if you look at the experiment, back at the experiments, you can see that if you look at the hydrodynamic regime, you see that as the pocket passes by, there is an increase in film, which is noticeable, but the friction doesn't change. But if you go towards mix and boundary, you start seeing that the effect of texture has a very small change of film, but there is some, and this small effect of the film has got a large effect on the friction, and this is what explains what Tom and Soren here had shown with experiments, the reduction in friction that you can get through the use of some very well-defined and shaped and oriented texture. So obviously not all textures will give you the right results if you don't know what you're doing. And this is actually just an example of how you do the other end of the scale models. You try to explain things, still microscopic effects that affect macroscopic behavior. Now, what I would like to do now to finish this is also to move on to a slightly separate part of tribology. What somewhat we neglect if we do lubricants. So people tend to say, okay, we need to model lubricants, but we need to model surfaces. We need to model how materials evolve as you rub things together. And in fact, there is the equivalent aspect we've seen with the lubricants, starting from the molecules that James has shown all the way up to how to look at fluid film, happen at the material scale. So in materials, especially if you have polycrystalline metals or ductile materials, the mechanisms for deformations are particularly important. And if you have these materials in a contact scenario, obviously you know that these individual asperities contacts, for example, will cause quite a lot of changes within your material. So one branch of what we do with the models is to try and understand how materials evolve in different scenarios. And obviously, even in this case, just like we've been saying from the beginning of this simulation, of this presentation, a simulation needs to cover a huge range of scales. So you need to go, taking an example from a different field in fractal mechanics. Everybody knows that in order to understand how a crack develops, you can look at it in different scales. You can look at the grain scale level, you can look at the dislocation motion level, and you can look at the atomistics of bonding and the bonding. And the same can be applied to tribology, where you can start looking at, for example, if you take a non-indenter, the indentation between a tip and a material will be governed by the interaction between a single asperity all the way down to the interaction between the dislocation under the indenter and the grain. And these are all things that can be studied, but obviously doing simulation in these areas, if you start, for example, looking at the atomistic perspective, requires quite a lot of power. And that is the power, for example, has been put in by some of my good friends and collaborators in Austria, two of which I think are listening here, where, for example, you look at trying to replicate a tribological contact at the smallest of the scale with atomistic simulations. And here, the way to do this, that can only be done really these days with this massively large atomistic simulation that Stefan set up for us and produced tons of results. You can actually try and replicate what happens in a real crystal with atoms, and try to, in this case, what he looked at was looking at two sets of polycrystalline metals and press them with a rough surface and slide. And the aim of this simulation was to try and see if what the atomistic simulation predict is similar to what is experimentally observed at larger scales, with the main interest in understanding what is that causes material transformations as you take the rough surface and slide it over this polycrystalline metal. And I think this is best shown with the video at the next slide. That actually we'll be looking at what happens. So you press down, and as you can see, as you press down and you increase the load, you'll see different things happening in terms of material transformation. So depending on the load you're applying, depending on the composition of your material, so in this case is a binary alloy of copper and nickel, you will get different things happening. As you can see, if you increase the load to a certain point, you get severe damage. Now, the whole idea here is that this simulation, which are particularly expensive, give you a unique insight in trying to understand if you can explain what happens in these systems. And certainly, for example, in this case, what we used it for is to try and build a map of behavior. So, for example, if you look at the map in the middle of the left-hand side of this slide, you'll see that you can see on the x-axis there is the composition of the alloy, and then on the left on the y-axis you got the amount of load you're pushing against the material. And you can see here you can start by looking at this map, identifying different regions, and the different regions correspond to something that can be observed experimentally at a slightly larger scale, simply because the mechanisms that we're looking at are those that we expect to see also at the larger scale. So, for example, in the green zone there, you when the load is just above the elastic limit, you start seeing twinning and rotation, the origins of the first initiation of deformation. And that is also observed experimentally for lightly loaded contacts, for example. But then if you go up in load in the yellow region, you start seeing that there is real transformations of materials. You start seeing grain boundary dominated phenomena with refinements that can be picked, again, both by the model and experiments. And as you go higher and higher, you can start seeing elongation of grains that precede larger deformation, which correspond to large-scale damage. And this is actually particularly beautiful because it, for the first time, shows how you can get those level simulation, atomistic level simulation, to explain things that happen microscopically. Now, as a last type of example, the other thing I would like to show is you can do very similar things if you look at a slightly larger scale. So if you look at models that allow you to study, for example, metallic coatings on substrates, and instead of looking at the atomistic simulation, you look at how the dislocations that are in this material move. So here is another example where you can take a description of a material and focus on what we believe is responsible for some of the results you see. For example, when you nano-indent a material, you see that indentation depends on the crystalline orientation, but also the dislocation structure of the system. So one of the things that Yilun Xu, one of our postdoc who's been with us for a few years, did was to use such methodology. So this is dislocation dynamics, is where you look at the evolution of a very large number of dislocation in a system and try to imply the plastic deformation that is a result of that. So this was used, for example, to show and describe what has been known in the materials literature for decades, which is the indentation size effect, which shows that if you start indenting a material which is polycrystalline, instead of getting a constant hardness, you have a decreasing hardness. And that is the results of the initial interaction between dislocation and the density of dislocation that you have near the tip. And then only after indenting for a large area, you start getting a constant value of hardness, which is what we usually refer to in these experiments. But also, you can explain how, if you have a very thin coating on a much harder layer, your hardness doesn't go to a certain value. It usually shoots off because it starts looking at the effect that the substrate has. And then by doing all this simulation, one of the things that we managed to achieve, which is, I think, it's very remarkable in the sense that allows you to come up with formula. So basically, allows us to propose a formula that allows you to study how the hardness varies across a number of length scales, both for systems that are, for example, hard on soft. So that's a nickel coating over on the left-hand side over a copper substrate, which shows and allows you to capture the behavior of these systems across the scale. So you've got a indentation side effect on the left-hand side, and then there's more standard continuum response on the right-hand side. And you can do that both for that regime or the regimes where you have something which is soft on hard, for example, where you start getting, as you can see here, a much larger indentation size effect on the left-hand side, and then you need to look at the more continuum type response at larger scales. So again, this is very important, and also shows how this simulation can give you a lot of insight into material transformation. And in fact, this same simulation were actually used now in combination with some of the experiments done by another collaboration of ours, Christian Greiner at KIT, who had experimentally observed already a few years back that if you take a single crystal copper and you slide sapphire only once over it with a certain load, you start getting this beautiful formation of material that is actually changed just over a thin layer, which is then beautifully separated from the rest through a trace line. And looking at this result, we thought, hold on a second, there must be something that happens in this system that must be coming from how this location move and rearrange those boundaries. So what we did, we took the same type of simulation we did for the coatings, and we started studying contact between this sphere and this material. And again, we first looked at what the size effect is, but ultimately what we saw, and you can see in many of these little plots at the bottom, is that as you take something and you slide it over, and if you account for the dislocation motion that are these little black dots in these diagrams, you see there's a clear formation of layers, these red bands. And these red bands seem to correspond very well with what the experiments were showing. And the way to explain that in the easiest possible way is like a stack of cards. You have a card, if you press on the top and you slide, you start forming a layer that doesn't rotate, because it slides over another layer that has got very large rotations of material. And that is how we described and how the dislocation is playing this phenomenon, which is really looking at localization of the formation over this red band. And that's how we believe that is the origin of this trace line. And again, the last slide on this I would like to show is that this can also be used to explain what happens at larger loads. So if you have apply larger loads and you do the same, obviously the material doesn't just form one line. It could actually form more than one line, and it can also start deforming, creating new grain structures, which is what Christian saw in other experiments he did. But also, this is exactly what happened also in your simulation. If you start applying more load and sliding more than once, for example, you start seeing this layer structure start forming a lot of dislocation accumulation that actually gives rise to, first of all, more planes, and then also to potential sites where grain recrystallization can happen. And this is actually very exciting, because it is a technique that allows you to explain a bit better how material transformations in tribology can happen. Now, as a last slide, just saying there is tons of opportunities in modeling will definitely come through looking at all the digital twin and in-silico experiments that we can do, as James said at the beginning. But also, I truly believe that collaboration through, with lots of people having different expertise and knowledge is at the core of us making real progress. And with that, both James and I will thank you for this and take as many questions as you like, really.
Thank you so much. Thank you so much. We're going to go over to Dr. Ben Beek from our sponsor, Micromaterials. A quick survey will come on screen, which will ask if you'd like to receive any further information for Micromaterials, and a few brochures will be released. So I'll hand over to Ben.
Thanks very much, Thackwid. I need Sam to do up the presentation. Thanks very much. Okay, so it's difficult to follow that great talk from Daniele and James. So I'm going to be talking just for 5 minutes or so about something new from Micromaterials, which is our new nano tribo test module for our nanotest Vantage system. And this essentially is a new multi-sensing reciprocating nano wear test, where we can combine the ability to measure contact resistance, friction, and depth all at the same time. And hopefully that gives us some insights into the material behavior. So compared to a conventional tribological testing where there's a multi-asperity contact and the contact zone is hidden, there can be some potential advantages in doing so-called single asperity tests, or nano tribology, micro tribological tests, where we're using a sharp probe as the tip, particularly with the nanotest Vantage, because this instrument has high thermal stability and high lateral rigidity, which means it can handle rougher surfaces better. And I'm just going to give a couple of quick examples in this about how we can use it. So for those that aren't aware, the nanotest Vantage is essentially a multifunctional nanomechanical nanotribological test platform, where we have a combination of test techniques available. So we can do nano indentation, nano scratch, nano impact, nano fretting. We can do those at a couple of different length scales. We can do the nanoscale right down to micronewton indents, or we can do equally right up at the microscale, right up to 30 newtons. So it covers this huge force range, and we can do tests in a range of different test environments at very high temperatures, at very low temperatures, and in a range of different humidities or fully immersed. So the nano-tribo test essentially is adding a fifth thing in there to this set of four. So what it's enabling us to do now is to perform these small-scale tribological tests, retaining the same level of precision on all these signals, but over much larger track lengths, and therefore we can go much faster and generate much longer sliding distances, and we can combine this with the different measurement capabilities in the system. So by changing the probe radius, we can really switch between single asperity contacts right up to more conventional multi-asperity contact tests. So to say, we retain the precision of the nano indenter for doing all these nanoscale measurements with the flexibility and the longest tests of the tribometer. And this can be used for a range of different things, from MEMS simulation, microtribological tests of biomaterials, and sliding interconnectors. So this is a typical example of where it's been used. So in reciprocating sliding of titanium 6-4, and in this system, it's a highly cycle-dependent and load-dependent response, where there's a transition to a brittle fracture mode, which occurs after a certain number of cycles at, in this case, above 40 millinewtons when we're using a 25 micron diamond probe as the slider. So as just as Daniele has just mentioned, essentially these sort of tests are very complicated. There's a lot of subsurface structural changes occurring, and in this case, there's a damage buildup. It's leading to the point at which the protective surface oxide is unable to protect anymore, and then you get this transition to this brittle damage regime. On the bottom, you can see the raw friction against sliding distance trace, and you can see the transition there. And then you can use these things to pull out quantitative friction loops automatically in the software in the system. So more interesting as well is to change also to blunter probes, and we can look at sliding interconnectors. In this case, this is a multi-layer thin film stack sliding against a 1 mil steel ball. And we can see here we're following the friction and the contact resistance here, and you can see in this case these two things are correlating quite nicely, and that the system is failing quite quickly. So again, it's a useful test for multi-sensing, is giving us more information. And my final experimental slide is just showing that we also have the stability for much longer and higher cycle tests. And essentially here we've got a 35,000 cycle tests at 200 millinewtons. And in this particular test, there's a couple of excursions where that metallic contact is partially disrupted with a high oxide debris that's trapped in that contact. And it takes, in this case, quite a large number of cycles to work its way out, and eventually works its way out, and you get a low resistance test. So these are bulk materials, so a bulk piece of aluminium, sorry, silver against a bulk slider. So this was just a very, very quick overview of this new technology. So we've got this new technology for rapid high cycle linear reciprocating nanoscale or microscale wear tests, where we can automatically record the friction, cumulative energy dissipation from friction loops and electrical contact resistance. And we retain the high lateral rigidity of the nanotesting, and that's a particular advantage that allows us the stability to do tests really up to, in this case, the highest so far is 300 meters of sliding distance, which is an awful lot for a nanoscale test instrument, and some interesting results on biomaterials and also alloys. And if you're interested in further information, please do look at our website for further information. Please download the tech note you see on the right, or contact us directly at microscales. Okay, so that's just a very quick run through, but that's it from me. Thank you.
Great, thank you so much for that, Ben. Begin to take some questions for our speakers.
Can I say something to Ben, if he's still there? Ben, we can model nanofretting. I just need to talk to you about it.
later then. Thanks.
We always like to bring our speakers together. Right, so we'll take the first question. Sam, can we have the question on the screen if possible? There we are. In the real industrial situation, to use traction drive, we need to ensure lubricant does not include wear particles. I think that's a bit of an observation. Is that correct to our speakers?
Don't know much about traction drives, to be honest, but yeah, I'm sure it's important.
Sure.
Well, I think it is very important. I think it is. I mean, I know a bit about traction drives, and it is extremely important. And I think that's where, again, making sure that you are in the right regimes of lubrication is extremely important. So, wear particles are also filtered, as you know, in most of these cases, but you need to be very careful about not having them. I guess that's an observation more than anything. I think, as you said.
Brilliant. Next question. If you do a simulation of mixed lubrication regime with traction drive situation, it is similar to understand wear particle entrainment.
Well, again, I think if I look back at doing, first of all, mixed lubrication regime simulation are very difficult, and in a certain way, you need to look at your traction drive situation in terms of what it does to the surface. So if you look at thinking about entraining a wear particle is in itself a fantastic complex simulation to do. For example, it's very difficult to look at interaction between wear particles and debris, and in fact, is one area where lots of people are making quite a lot of innovative modeling, because you need to look at interaction between the wear and the roughness and the lubricant, and now it's all entrained. So, for example, I've certainly done some simulation where we've looked at accumulation of wear debris on the inlet of the contact, but looking at the actual interaction between the wear particles in the contact is a particular challenging, even at any level you look at it, basically. So it would be nice to be able to do that. Maybe we need a student or two, I think, on that.
Brilliant. So we have the next question. Dr. Ewan, if the computational shear rates used are comparatively higher, then do the simulations correspond to the same lubrication regime while sliding, like simulating a boundary lubrication?
Yeah, so I guess an important distinction is that we don't have any entrainment in the molecular simulations. I mean, we're basically looking at the center as the contact, or at least kind of average conditions within the contact. And yeah, you only have as many molecules between the contacts that you put there. I mean, there are ways that you could try to study entrainment with things like the grand canonical molecular dynamics technique, but it would be extremely expensive, and it would have to be a nano contact, even if it were. So essentially, yeah, you have to say how many molecules are there at the start. So you have to essentially, we measured film thicknesses, measured where roughness starts to affect it, and then used the kind of minimum film thickness that we could to make the simulations as computationally expedient as possible, without kind of having any surface confinement effects for these simulations. And for the boundary ones, yeah, they're in the boundary lubrication regime, because yeah, there's not going to be anything entrained in the surfaces.
Brilliant. Thank you for such a good answer. Have you ever considered such wear particles entrainment effect on viscosity reduction or abrasive effect for mating surfaces?
Well, again, let me take that in the sense that if you go back to what I said before, it's very difficult to do direct simulation of wear entrained into contact. What certainly can be studied is to look at the effect that this particle might have on the viscosity changes. But then again, that is only a bulk level. So when you look at what happens in the thin layer of lubricants in the contact, it gets very tricky to look at exactly what the effect of, and also looking at the distributional size of wear particles. It's something that can only be done statistically in some respect. But the mechanism certainly that happen there is changing the perceived viscosity of the fluid as you do that. But specifically, there will be a lot of interaction between asperities and the wear debris. So these must be captured if you want to know what wear does.
Brilliant. At James, lubricant film formation is obviously very important for preventing wear in components for a gearbox. Could you use the EHT models to estimate the thickness of the film a given fluid would form, and therefore what the lambda ratio would be in operation?
Yeah, I mean, that's something that, I mean, that's more of a question for Daniele, really, I guess. But that's, something we commonly do is either measure the film thickness in an optical interferometry rig, and then, correct to the surfaces that you're actually using in the friction experiment, or predict that with a something like a Hamrock Dowson, or, I mean, fairly controversial area on what model you use and what parameters you use. But that's something that we commonly do for lots of different systems and conditions.
Yeah, so again, one of the things that you need to add to that is that if you do the EHT modeling, then you need to be very clear about what you're doing about the rheology of your fluids and how you model it, and how everything affects your response. So again, doing those models and how to get the right answer depends very much on what you know about the system, both from the lubricant point of view and the roughness, the lambda ratio, as you said.
Brilliant. Dr. Yuan, is it assumed that continuum laws break at the molecular level, then which a load friction relation is better suited to predict the coefficient of friction for the MD of frictional sliding?
So I mean, many continuum laws do break down at this level, but one that holds fairly well for at least for the systems that I talked about today is the kind of a Monton-Coulomb friction law for kind of a linear increase in friction force with normal force. So that one holds for these systems actually quite well. We've done some work with rough surfaces where it doesn't hold so well. So you do get an adhesive component to the friction, but it's fairly easy to account for that with something like the I can never pronounce it, Derashewin offset. Not too good when we're Russian, but essentially, in terms of the friction to the normal force, that one holds fairly well for the systems that I talked about today. So it makes it fairly easy to get the friction from the shear stress data.
Great. We'll move on to the next question. In real applications, modeling usually struggles to simulate additive tribofilm formation and how this affects frictional wear. Do you have any comments on how we can improve this in future models? Without this, you would still need to rely on experimental methods. Thank you, Rob.
Yeah, so that's a big area for sure. So anti-wear additives in particular, where you're forming thicker films than the ones I talked about today. You form typically hundreds of nanometer patchy tribofilms, which are basically they're mostly polyphosphates, and they act to reduce wear between the sliding surfaces. And the formation and removal of those is extremely complex. And again, if you're in a mixed lubrication regime where you've got only some asperities coming into contact some of the time, then it becomes a very complex problem in terms of trying to physically model that process, because there's an element of randomness in terms of the solid-solid contact and how frequently that occurs. So there are ways that you can kind of empirically treat that in terms of experimentally measuring tribofilm formation rates under different conditions and tribofilm removal as well. So there's several groups who try to do that in kind of an empirical way, and that's probably the best we can do from now, because of this kind of mixed problem. It's very difficult to do anything kind of more thorough than that, and that's where these kind of data-driven approaches in this mixed lubrication regime could well help quite a lot. When you've built up enough experimental data to train these models, that's where these kind of joint approaches start to become quite useful.
Yeah, can I just add maybe that sort of this fast indentation mapping now capability that we have now allows us to sort of map over these wear scars, and when the tribofilms are sort of at the order of sort of 100 nanometers, then you've got a really good chance of basically mapping mechanical properties and inferring from that presumably also indirect film thickness measurements because of your they're
Exactly.
mechanically different from what's underneath.
The mechanical, exactly. What happens to this film and what these films are, it's very important. So their properties is extremely important. I mean, obviously, as James said, having a lot of data to try and look at what happens is very important. The other thing we're doing, we have a lot of activities on mechanochemistry just to try and understand exactly what happens as what triggers the formation and how these things evolve. But obviously, if you want to do that for any class of additives, you need to do a lot of molecular simulation to understand what happens to each of them. So there is a good balance between trying to understand the physics of something of a specific phenomenon and trying to understand what happens to a large class of additives, where I think using a lot of experimental inputs will be useful. We're modelers, but we know what models are limited.
Brilliant. Should we move to the next question? Professor Dini, chemistry is strongly dependent on temperature. Do you think that flash temperatures can affect performance of lubricant additives? And if so, how to model?
Well, yeah, I mean, flash temperature, I mean, whatever you want to call them, temperature rises due to interaction between surfaces are extremely important. I mean, their effect could vary from enabling to form something on the surface to removing something from the surface or decomposing what is formed on the surface. So certainly, temperature is almost as important as pressure in this equilibrium between the chemistry and the mechanics here. So it's, to me, absolutely important to try and understand what it is. And in fact, both in the mechanism of film formation, if you're talking about something that forms on the surface, and in the understanding of what the temperature is through the large-scale models where you try and get what the temperature is, these are very important factors. Otherwise, guessing what lubricants and additives do is difficult.
Brilliant. Thank you for them answers. I think that's all the questions for now. So on that note, I want to thank everyone for your questions. I want to thank our speakers, Professor Dini and Dr. Ewan, for such an engaging talk. Thank you for sharing. Really appreciate your time. I want to thank Micromaterials for supporting this webinar. And a reminder, you can watch this video again on our website at surfaceventures.org. So please do visit it. And we will organise our next seminar towards the end of the month on the 25th of March at 2 p.m. So please stay tuned for further information. So on that note, we'll see you next time. Thank you for joining us today and enjoy the rest of your day. Thank you, everyone.
Yes. Thank you.
Bye.